So just to show you where we're at, whoops, we are going to try and be right here. What page is this? Page 85. And also thank you for participating in that survey. I appreciate you guys all doing that the other day. That gave me good information. All right, so here's what we're talking about. Capacitance is defined as the ratio of charge to voltage, right? So let me just do it this way. So that's where, if you want to follow along, ooh, we got the triple equal for is defined as the ratio of charge to voltage. Now, if you think about this, let's say I had two pieces of metal here, right? So let's say this is a metal disc. And here's another metal disc. So again, they're three-dimensional there. Okay, the idea is how much charge can I store per unit of voltage? So if I have these two pieces of metal, the amount of charge I can store per volt varies based on how close they are and how big they are. So that's it. It's the charge to voltage ratio. Now, I don't remember this equation this way. When I was a kid, there was a shopping network called Q equals VC. And so that's how I remember it. I don't know if they still have that. I don't care. But so you're going to hear me say this, QVC, the home shopping network. Evidently now there's HSN, which is the home shopping network. My students taught me that after. Yeah. So back in the day, there was only QVC. Now, delta V, there's a difference between V and delta V. So delta V is potential difference. So obviously, we're not going to have charge stored if these, so let me put it this way. Let's say this one was at plus 3 volts, and this plate over here was held at negative 3 volts. Obviously, we'd have, and let's say this happens to be holding 6 microcoulombs, and this would be negative 6 microcoulombs on this plate, and this would be plus 6 microcoulombs on this plate. And how would I do this? Maybe I do this by connecting these two things with a wire to a lantern battery. So a lantern battery maybe looks like this. And so this would be the plus terminal. This would be the minus terminal. And the idea is by applying a 6-volt battery here, you could cause these things to separate. And think about this. Which charges are most likely to move around in a circuit when everything is made out of metal? What do you think? Negative. So the idea is, what does a battery do? The battery acts like a pump, and it pushes electrons from this plate over there. And as a result, there's an absence of electrons here, leaving 6 microcoulombs of excess positive charge. And there's a bunch of electrons bundled up over here. And that would leave. And so if we knew these numbers, I could punch it in. Oh, I didn't mean to do everything 6s, but whatever. So in this particular case, delta V would be 6 volts. And now, just so you know, it turns out we do not take the total charge. We just do the charge that was moved. So in this case, that would be 6 millicoulombs. All right. And so again, you take the charge on one plate, and the convention is just take the one on the positive plate. So we see that if you apply a 6-volt battery here, you could separate 6 microcoulombs of charge. So what do we get? 1 microfarad. All right, 1 microfarad. F.
Do you think you can redo this problem with different numbers? I'm getting confused with the 6s.
All right, let's say this was.
You're just waiting for me to move?
No.
Yeah, dig it. That was cool. I kind of feel like we just joined Pink Floyd. Hold on. How about I try this? I got a simulation ready, and I think that'll help, Nick. Because you're right. That was a bad choice of numbers. I didn't mean to do that. So let me see if this one's good enough. Actually, let's go to. Give me a sec. Yep. This one? All right. So here we go. So let me try this again. Let's say I put a 1.5 volt battery on here. The idea here is this is how this happens to turn out for this particular case. So this thing that I'm wiggling right here that says voltage and it's orange and black, that's called a DMM. And we're going to be learning about that in lab tomorrow. Okay, so this is talking about a voltage measurement. It is not reading the potential of one of these plates, it's reading delta V. So this says, hey, if you put a 1.5 volt battery on here, I'm going to get 1.5 volts potential difference across here. And commonly what we'll do, now some of you out there, this might be easy for you, but I still encourage you to stick around at least for the first half hour, okay? And then if this is all easy, make sure you do every single workbook problem in this chapter to find out there's some tricks, okay? So do not get overconfident here, but do the practice and you guys are going to rock this stuff. So usually there's some point in the circuit that we call 0 volts. If this is too easy for you, just stick with me and be bored, okay? And take the easy points. Now, according to this, delta V of the battery is 1.5. That's the particular battery I chose, all right? Now, it's just like gravitational potential energy or the electrical potential energy. I get to choose where I call 0. Normally, we pick the negative side of the battery to be 0 volts. That way, we get the lowest potential in the problem, 0. This spot up here would then be at 1.5 volts. All right, and so the idea here is the voltage at the top is 1.5. The change in voltage going up here is also 1.5. Now, if I go this way, the change in voltage would be negative 1.5. But typically, when we're writing this out, we just write the magnitude of that change. So it's going to change by 1.5 volts going up on the left, and it's going to change by 1.5 volts going down on the right. Okay, more on that later in the semester. For now, we're going to kind of be loosey-goosey with polarity, meaning plus minus signs on these delta V's. For a short period of time, we could just talk about the size of it. All right. Now, in this case, this particular example shows us, whoops. There we go. So in this particular case, we could see that what is this capacitor really storing? You want to say it stores charge, but I'd really say it's storing energy right here. So the idea here, and we'll get the formulas for this in just a minute, but so Nick, is this giving you a slightly better idea here? If we know that you have a 30 picofarad capacitor, pico is 10 to the minus 12th, and you apply 1.5 volts, we end up with about that should be 0.45, but there's probably a numerical artifact here. So there's rounding errors in here. And that's basically, oh, why did I do orange? Yeah, green. Nick, is that helping a little bit on that?
Yeah, thank you.
Yeah, and so that's great. And we're going to get to more complicated problems in just a sec. So cool. And now notice one of the things that's going to be, I want you to start thinking about this example and just kind of remember this. Let me do this. All right, let me disconnect the battery for a second. It's still on my annotate. There we go. I'm going to disconnect this thing, and actually, let's just reset it. Too many Zoom. Let's reset. Okay, so now the idea is this. Geometry determines the size of C. What do I mean by that? If I change the size of this thing, do you see the capacitance changing up there? So the bigger you make these plates, the easier it is to store charge, the bigger your capacitance gets. Said another way, right? The bigger you make these plates, the easier it is to store energy in the electric field between the plates. Now, here comes the next one. What if I bring the plates closer together? Think to yourself, it's okay to be wrong. But think to yourself, if I bring the plates closer together, should it be easier or harder to separate the charges using the battery? Okay, so let's see what happens here. If I bring them closer together, look, the capacitance actually goes up. So when they're far apart, you have a very small capacitance. When they're close together, I like to think about it like this. Let's put the battery back in. And so now I'm going to turn it on. And let me see here. Maybe I'll try and get this to exactly 1 volt. So that's one less thing to think about. Hey, I happened to get it exactly. That's pretty odd. All right, so notice we have 1 volt here. Let's just put this over here for right now. Okay, so we have 1 volt between these two. If I can keep this on here. There we go. 1 volt across the battery. And now watch what happens. As I bring these 2 plates closer together, I'm going to bring them closer together. When I do that, think about what's happening here. When you get these plates really close together, it's basically just like a very strongly polarized system. It's actually easier for the negatives to move from one end to the other because there's that strong electric field that's attracting them once they get all the way around. So you could actually hold more charge on these plates when they're close together as opposed to when they're farther apart. All right, so let's just make this thing as big as possible, right? And so now we're going to have this huge, in this case, we have a huge amount of charge. Well, not huge. Picocoulombs is actually pretty small. So this is a small capacitor, 1.7 pico. All right, so that's just your basics on here. Why are we going to learn about this? Now, I know this is kind of jumping ahead a little bit. We can't really do this yet, but here's why you care about this. In practice, what's something you could do, right? You could charge up this capacitor, and then you could remove the battery, and then you could take this capacitor and connect it to a light bulb, and you get some light out of it. And the idea is you're going to use up the charge or use up the energy that's been stored on the capacitor. So again, looking at this, the idea is here I am, I have a charged capacitor. Energy is stored. So try to think of this as energy. And then I'm going to release this energy in the form of light right now. And so that's what we're trying to do here. And let's go back to here one more time. Let me spread these out a little bit. The idea here is you could also see the electric field. And so again, if you take these capacitor plates, right, they produce an electric field between the 2 plates pointing from plus to minus. Something that's very sneaky here in this chapter in general that is we're going to save for Wednesday's lecture. I just want to point out how very different this situation is when I do the following. Watch this. Let's say the battery is connected in the circuit and I change the geometry. We see that capacitance, charge, and energy are all changing. Do you agree? I hope you do. Now, what if it's disconnected? If it's disconnected and I change the geometry, the capacitance should change. However, there's no circuit. There's no way for the charges to flow. Think to yourself, if I change the separation, what should change with the amount of charge? And what about the energy? Let's see what happens. Ready? There's nowhere to change the charge. And notice this weird phenomenon happens. When the battery is disconnected, you crank up the capacitance, but you have the same amount of charge. That implies you have a smaller electric field and thus less energy. And so, yeah, that's kind of crazy, right? So look at the amount of field lines, right? Oh, well, I guess you can't really see it because it's too, yeah, anyways. All right. So that's something I want you to watch out for. Let me pause for a second here. Is that making any sense? This is just kind of a conceptual overview of what capacitors are good for. All right. Okay. And at any time, go ahead, Ryan.
If you were to move take the geometry of it, move them farther apart from each other, the capacitors, while it's disconnected from the battery, would that also cause the stored energy or the electric field, I mean, to go down?
Let's see. So let's think about it. You have the same amount of charge on here, right?
Mm-hmm.
So, I guess we should be careful here, right? So assuming the amount of charge doesn't change, does the charge density change?
No.
No. So if the charge density doesn't change, will the field between the plates change?
No.
No, because it's constant in there. So I don't know exactly what I said earlier, and maybe I misspoke because it sounds like I implied something that I didn't mean to. So the idea is this, but what I did mean is this: if it's connected and then you bring it closer, right? See how the field changes?
Yeah.
That makes sense. So I guess if I misspoke earlier, what I was trying to say is basically the situation is very different whether the battery is connected or not. And certain
Mhm.
things can change when the battery is connected or not. And we'll focus more on that in the next class. Is that good for now?
Yeah.
If there's no way for charge to come on or leave the plates, we expect sigma to stay the same. The electric field is sigma over 2 epsilon for a single plate, sigma over epsilon naught for a pair of plates like this. So we expect the electric field should be constant as you change it if disconnected. We expect it to change if connected. Is that good?
Okay. Yeah. That makes
Yeah.
sense.
And I hope I didn't misspeak earlier. Every once in a while I do that and I apologize. So good
No, I
question.
think you're.
All right. Other questions? Right on. And you can throw it in the chat too if that's your style. Let's get to here. All right. Let's try to understand the math behind this simple case right now. Okay. So let's look at 25.1, and I'm going to try and draw this up because this is the one we're trying to understand. So I'll get my whiteboard aligned in just a minute. I'm just trying to draw this one here. All right. Positive sigma, negative sigma. Area is A. All right. Okay. Oops. Okay, so we got this situation right here. All right, so in this case, whoops, this is, hopefully you agree that the electric field inside here is sigma over sigma over epsilon naught, because we have two of them, in the negative I hat. Let's pause on that for a second. I expect the electric field to point from plus to minus. So from the high voltage to the low voltage. So that's the electric field direction, right? Okay. And so because there's sigma over 2 epsilon from this one and sigma over 2 epsilon from that one, that seems reasonable. So far, so good. Now, and this plate spacing, I'm going to actually move it up here so I have a little bit of room to work. So we got some spacing there. Great. Next part of this question says, use this integral. So we know that the change in voltage between these is minus the integral of E dot ds. Okay. Well, in this case, what's the logical direction to travel between these two plates? Up and down? No. In a circle? No. How about to the right? Let's go from this plate to that plate. All right. And so why would I choose to go from the negative to the positive? Well, I just know from experience, this is what I like to think. If I go from a negative plate to a positive plate, I expect to go up in voltage, which means I expect all my minus sign crap to cancel out. So that's why I chose to do it that way. So hopefully this makes sense to you here. The change in voltage between those two plates is minus the integral of E was sigma over epsilon naught in the negative I hat. And then I'm going to dot that with, well, in this case, why don't we just travel this way? We're going to go this way, which is dx in the I hat. So that's ds. And lo and behold, what do you get? This drops out. This dotted with that is equal to 1. I hat dot I hat is 1. And so sigma over epsilon naught is a constant. We're going to get sigma over epsilon naught times the integral of dx. And I'm going to integrate this thing. You could choose, it looks like in the picture, we started maybe right here. So this was x equals 0, and this is going to be x equals d. So my limits are going to be 0 to d, which notice I get sigma d over epsilon naught. So that is the potential difference between the two plates. Said another way, that's the voltage across these two plates if they're going to have these two surface charge densities. So if you're going to tell me what sigma is, I could say, well, you'd better apply a battery that's this big. That's weird units, but that's volts. All right, just hang with me. Okay, we could do the units later, not now. All right. Next, what's the next part of this question? Determine capacitance. Okay, I've run out of room. I need to erase this. So up here, I do know that both plates are area A. That's going to come in handy, okay? Capacitance is defined as charge per unit volt, all right? So here we go. Let's see what we get. Well, this is Q divided by the change in voltage, which was sigma D over epsilon naught. Huh. Doesn't look very inspiring. Two of these symbols are related in here, though. Which two?
Q and sigma.
Q and sigma. So what's sigma?
Q divided by A.
Yep. So that's how you get the Q out of there. All right. And so now why not just multiply by the reciprocal, right? So we're going to get Q times I know this is going to shock you. Take a look. We see that capacitance for a pair of plates is A epsilon naught over D. Notice it depends only on the geometry, not the battery, not the charge density. If you do the math and work it out and are careful with what should cancel, we discover that the capacitance is purely related to the shape of the pieces of metal I use to make the capacitor. That's a big deal. So you could think of capacitance as being some geometrical measure of how good things are at storing charge. If you take an arrangement of two pieces of metal, any two pieces of metal, it doesn't even have to be metal. It could be a radio antenna and your hand has capacitance. Your hand could be like one of the plates and the antenna, just a rod sticking up, it would be complicated. I don't know how to calculate that right now, but I do know that it would relate to the distance we're spaced and about in the area. So if you could think of this conceptually, this is a huge deal to remember. The bigger you made the plates, the more charge it could hold. The closer they are together, the more charge you can hold. And then remember, holding charge is the same thing as storing energy. That's more fundamental, storing energy. All right, the rest of this problem, big deal. You could do it at home, and I think you could learn that. So let's just put it up on the screen so we could see it. And I just want you to realize that, oh yeah, I can rock this out. So here's this. You could stick in some numbers. Now, this is probably worth mentioning here, part G. If you get to 3 million volts per meter, you run into trouble. You get a spark. So most capacitors completely fail at some point. Air shouldn't let the charge flow. Yeah, it does. It's totally a theremin. The idea here is this. If you get the two pieces of metal too close together, the air actually changes from an insulator into a conductor and then sparks fly. And so it turns out most capacitors in the real world will have what's called a breakdown voltage, where if you exceed that voltage, the capacitor is probably going to be permanently ruined, or at least have a spark and potentially be ruined. And so, yeah, that's a problem. So if you want to learn about that, that's great. You can get these charged. And so I think this is a good problem to do to get started for you guys after this class is over. It's pretty easy, but you can get the numbers and kind of get your feet wet with that. Any other questions about that? Is that making some sense? Maybe. We could look at another one, right? So there's 3 common geometries. We did plates. What are the 2 other geometries we've talked about all semester?
Cylinders.
Cylinders and spheres. Cylinders is probably the most important one because coaxial cables are used all the time. And we need to know the capacitance per unit length for coaxial cables. So that's the next page. Let's take a look. All right. Now, so I'm just going to scroll down here. The first one is for spherical shells. It turns out you could see this. There's a really cool thing here in part D. I'm going to leave this one for you guys to do at home. Okay. What if the outer shell is really large? And then there's this one, 2 conductors that are made from cylindrical shells. And so notice you have some line charge density stuck on those. This is a coaxial cable. And so if you want to know the capacitance, usually for these, you can get the capacitance, but you could also get the capacitance per unit length. And so if you have 20 meters of cable, you could just quickly multiply that by 20 meters and get the total capacitance. And so typically cabling is rated at capacitance per unit length. If you want blah, 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 you could do this one. And I want to point out one more. Here's 2 wires. If you have 2 wires in a circuit, you could do this one. Now, I do have my list of recommended problems here, and I just want to point out, I got to tell you guys, this stuff is really useful if you're going to be an electrical engineer, and you should probably do it if you're going to be a physicist. But other than that, we're going to focus more of our energy on the circuits part, okay? And this one in particular, I thought it was really cool, okay? But it's not required. So this one is particularly challenging, all right? So you may want to skip this one. The other ones are required, do them, but don't expect this to be a huge focus of the test or the next quiz. And I should confirm that later. What's up, Rye?
So this might be a dumb question. I'm not sure, but so I can totally see.
Well, wait, Ryan, it is coming from you, so.
Ah.
So it's clearly
Nice,
a stroke
nice.
of genius. No, what's up?
There
What's
you
up?
go. Oh, okay.
Sorry about that. That was cold.
No. So I can see like practical applications with the cylinders and stuff like that. But what about like practical applications for spherical shells and stuff?
Yeah, they would use these for. I believe there was a saltwater, a salinity test that was made using that device. Or you could also make. This relates to the Van de Graaff generator because the Van de Graaff generator has a dome on top, and actually, I think it's probably more related to the last part of it, part D. Anytime you have a metal sphere, it has capacitance. What? You're like, where's the other plate? It's at infinity. And so yeah, there's this weird. Let me show you what I mean here. So I know this sounds really crazy, but basically you could actually use this to consider this. It turns out the capacitance of a single metal sphere without the other one there is not 0. And so that you could try and use that to understand the capacitance of some arbitrary metal object that's in the room. And how is that going to affect your radio reception or things like this? So there's weird applications to this. I don't know if I did it justice, but I think somewhere in here I might have even suggested the main one that comes to mind is I'm thinking of maybe that seawater salinity thing, but you could also do that with cylinders, right? So is that good enough for right now?
Yeah, that's pretty cool actually. Okay,
yeah,
cool.
and I think more important is it gives you a chance to practice all 3 and see that they all have a pattern.
Yeah.
So yeah, that's more
cool.
Yeah, I gotta agree with you. Cylinders and plates are just so much easier to use. Yep.
Yeah. Okay.
All right. Good point. Yeah. All right. So that said, how how about we take a break right now and come back in like 7 minutes, and then we'll start up with the circuits. So just to show you where we're going to go next, and then you can decide if you don't want to come back or not. So I'm going to start talking about series circuits and parallel circuits with capacitors, and that's what we're going to spend the rest of the day in class on. I cannot emphasize this enough. If you're going to take off because you've done circuits already somewhere, that's fine. Do not underestimate this chapter if that is you. Make sure you do the practice, because I do things a little bit differently sometimes than other people and maybe use slightly different symbols or whatever. It's important that you do enough practice so that on the quiz you're fast. And just because you did it once doesn't mean you can still remember it. So, all right, so let's take a short break and we'll come back after there. All right. So yeah, I've got to use the restroom real quick. All right. Okay, let's see. Oh, there's lots of interesting chat here. Mm,
I have a question when you're done reading the chat.
yeah. Capacitors are used a lot of time. You can store energy, you can flatten out curves, you can use them to create oscillators and receive or transmit signals. I mean, there's a lot of applications. Yep. You can use it to make an AC to DC converter, part of it. Yeah. So the capacitors are used in number. And by the time this class is done, you'll see kind of where they would be used. So yeah. Who was the question?
Ori, I was
Oh,
just thinking.
what's up? Yep.
With coaxial cables, if
Mhm.
you have a higher capacity in the cable, you can put more electrons through it at any given time. So you would have a stronger electromagnetic field, which is why there's like physical limits to copper wiring, right?
Yeah. So
It's
we
more
got to be
complicated than
careful.
that.
Well, we got to be careful. So with a coaxial cable, usually, let me just draw, or whoops, let me not do that. Let me do this. So yeah, you got to be careful. Normally with a coaxial cable, we think of, right, there's some like stainless or copper or aluminum, some kind of sheet there, and then there's a central wire here. So that's why in those Gauss's law, I kept trying to do the central wire, and just to make sure you can see that that's not making contact. So this is coming out through the center. Now current is going to travel this way and then actually this way through the outer conductor. So current is flowing along the surface of this, coming back this way, and then on the long. So you're not transporting charge from the inside to the outside.
Got it.
That said, it has the potential to do that in theory, which means there's some capacitance between here and there, even though that's not the direction charge is traveling. And that capacitance can affect the ability of this wire to transmit certain types of signals that have a changing frequency. So AC signals. More on that at the last chapter or so. So how about I just leave it at that? Is that okay?
Yeah. That
Yeah.
works.
Yeah. So it's complicated, but clearly we see that if you had a potential difference between the inner and the outer, which you may well have, you could actually have breakdown and have current flowing the way you don't want. We want current flowing this way. If you apply too much voltage, it might actually flow inwards and outwards radially, and that would be maybe undesirable. So we learn about the capacitance of these so that we can avoid that undesirable effect and control for these frequency response issues. That I'll leave at that. That's really complicated sounding. Just basically, it's tricky. Yeah, that's short version. All right, good question. So yeah, let's see. Let me do this one and go to here. Oh, and so, okay. So what I want to do right now is talk about this, and we're going to start with the simple parallel circuit and a simple series circuit. And what we're going to do is we're going to learn that you can make an equivalent circuit out of this. So the idea here is this capacitor and this capacitor. This is how you might wire it in the real world. This is the symbol for a battery. This is the plus terminal. This is the minus terminal. The thick black line is the minus terminal. There are other ways to do this. This is one way. Script E stands for EMF, which basically means the potential difference across the battery. But you could take these two capacitors and combine them into a theoretical circuit that only has one capacitor. Same thing you could do with two capacitors in series. You could combine them into a theoretical capacitor here. So we're going to try and understand real life circuits that have lots of capacitors in them by simplifying them to these equivalent capacitors. Okay, that's going to be what we're going to start with. Now, the rules for doing that are right here. If you have capacitors in parallel, you just add them up. If you have capacitors in series, you 1/4 add them up. That's a very technical term. All right. The idea is 1 over the equivalent capacitance is 1 over C1 plus 1 over. And this one tricks people because you got to remember to flip it upside down when you're done. Right. And more on this in a minute. You'll see. Now, there is a shortcut that's great for 2 capacitors. And I can derive that for you later. But just know this is a shortcut for 2 capacitors. These are some interesting new rules that we need to learn as well, right down here. So if you have capacitors in parallel, so again, all of this crap here is for parallel, all right? And all of this stuff over here is for series. So in this one, you can see that if you have 2 capacitors in parallel, they have the same voltage as the equivalent. And their charges add up. Oh, whoops, I'm using the wrong color. My bad. Here, all 3 capacitors would have the same, the equivalent and the 2 capacitors that comprised it. So in parallel, same voltage. In parallel, same voltage. Remember it that way. In series, same charge. So that's how I remember it. In series, same charge. Why? I remember it this way. I know that for resistors, which we're going to learn about in the next chapter, resistors in series have the same current. So current relates to charge. That's how I remember it. I know that doesn't help you too much yet, but so this is how I remember it. So there's a difference. When you have parallel capacitors, they have the same voltage as each other. When you have series capacitors, they have the same charge as each other. And then in both cases, you add the energies to get the total. All right. And we'll do an example here in just a minute. And then in all cases, here are the equations. Notice this is a little bit different, this particular one. Somebody asked about this last time, but notice the energy equation here, right? There's a factor of 1/2. It's not QV anymore. So this is the energy stored in the capacitor. So that's why there's a subscript C. There's a 1/2. Why is that? It's really easy to store the first charge on the capacitor. But then as you get more and more and more on there, it gets harder and harder. Similarly to just how a spring force keeps increasing, similar to the spring energy, which gets a 1/2 from calculus, the same thing holds true for capacitors. Here's our home shopping network. Great. All right. Now, one thing you really got to watch out for here is the following. Even in this simple case, whoops, where's my, if I go up here a little bit, let me see if I can get these both on here. Let me get this just a little bit smaller. There we go. This should do it. All right. So I want to point out this important fact that people tend to screw up. The voltage of this battery here, delta V of the battery, is equal to E in this case, okay? That's just pretend E is some number. Maybe it's 1.5 volts. Notice delta V of the battery here, this is just like our last circuit that we looked at. That's going to be the same voltage across here. If I start out at 0 volts at this point, I know that this is still at that point, so they both have 0 volts. If this is 1.5 up here, I can see that I have 1.5 volts here. The switch doesn't do anything, so I'd still have 1.5 volts here. And notice both the equivalent capacitor and the battery have the same voltage as each other. They both have the same voltage. However, when I look at this circuit up here, I see that the 2 voltages do not equal the voltage of the battery. Look carefully down here. Those 2 voltages will add up to the voltage of the battery. So in this problem, delta V2 is going to be some number that's not equal to E. It's some fraction of E. Delta V1 would be a different number. It's less than E. So if this was 1.5 volts, I could imagine that this might be, say, 1.0 volts, and this one down here might be 0.5 volts. So you can get different voltages in these problems. The voltage across the battery is not necessarily the same thing as the voltage across the capacitors. You need to watch out for that weird little fact if you're doing the math. It's so easy to just grab a number from the battery and shove it in. That's not going to work for you. All right, I've been talking a lot here. Why don't we do a problem and I'll show you how this works out. It probably doesn't make any sense right now, okay? So let's go down here and look at this one. I'm going to try and look at this problem right here, 25.5. And so you could get this thing drawn up, and I'm going to check something here. So I want to see if I happen to have, if I drew it up in the solutions, because I'm worried I'm going to run out of space. Typically solved in class. Good. So let's do this one. All right. So we better make sure we get this one done. Okay. So just getting you back to where we were. I'm going to start with this problem here and try and draw it up. I'm going to run out of room, but I'll do the best I can. So we may have to, yeah, let's just do the best we can. All right. Okay, so I've got it drawn up there. And so if you want to work ahead, that's fine. If you want to just tune out, or if you think you got this, go for it. And I'll be trying to check this one as well. So now here's the idea. We have this complicated thing. We have rules for one series circuit and one parallel circuit. Now we've got a mix of series and parallel. So the trick is, if you have an actual circuit, we try to look for some part of the circuit that looks either series or parallel. So in this case, I'm going to call this the main branch, the lower branch, and the upper branch. Again, I'm calling this one the main branch, the lower branch, and the upper branch. What looks like the most doable place to start this mess? What do you think? Upper, lower, or main? Which two capacitors look like they're the easiest to maybe have a rule that we can find?
The main branch.
The main branch, I wouldn't go that way. That's a good guess.
Lower branch?
I wouldn't go with the lower either. I would go with the upper. And this sounds crazy, right? This is actually the most complicated looking piece, but take a look. If I just think about these two, aren't these two in series with each other? They're right. They look exactly like, and so you can see why we got to do this, right? Right up here. If I scroll up here, what I'm saying is this part right here looks a lot like the upper branch. And that's why I'm going to start with that, because everything else, it's like, that looks too complicated for me. Does that make sense why I chose to start here? I don't know. We'll get used to it after time too. So let's just force ourselves through it. So these two look like they're in series to me. More on that later. Okay, they're end to end. So I'm going to combine those two. So what was the rule for combining them in series? Well, I know that C12, I'm going to use the shortcut from the previous page. I'm doing a series combination. So I'm going to use this rule. I'm going to use the shortcut, or you could use this long way if you want. But since I have two capacitors, I'm going to do it like this. Let me get back. I'm using that rule. Let me write it here. If you have 3 or more, just the long way is faster. So in this case, it's going to be a 5 micro times a 15 micro divided by 5 plus then, that's 20 micros. Notice one of the units of microfarads drops out. This gives me what, a 4? 15 divided by 4, isn't that 3.75? It's almost 4 into 16 would be 4. So what that says is these two capacitors in series are equivalent to one capacitor that is this size. Aha! I've suddenly made the circuit a little bit easier. I've taken something that had 1, 2, 3, 4 capacitors, and I'm going to reduce it by 1. So what I'm going to do there is say, well, now I have a 3.75 microfarad right here. So that's the upper branch that we just worked on. I still have the lower branch here, which was 8.25. I still have the main branch, which has a 24. And then somewhere over here, I'm going to stick the battery over here just so I have enough room, okay? This is plus, this is minus. All right. So if you had to guess, which two capacitors would I probably work with next? This blob over here, right? I'm like, wait a minute. What does this look like? These are in series, or does it look like they are in parallel?
Parallel.
Parallel. Excellent. Nice. So in parallel, what do you do to get the equivalent capacitance?
You just add them.
Right. And so what is that? Is that going to be 12? I think it is, right? So in this case, now I have 12 microfarads from combining those. I still have the same branch here, 24. Still have a 1.5 volt battery. And so now I'm up to these two. I got to combine these two, running out of room. Whoops. Come on. So now you could probably think we're going to do a series combination. These two look like they're in series. So that one I'm going to write down. I'll call this C. This is what? I don't know. This is all of them, right? Oops, I'm running out of room. How about I just say CEQ? Let's use a different color. CEQ is equal to, what is it? 12 times 24 over 12 plus 24, which is 36. And we're going to get microfarads. Again, one of the micros are going to drop out. And you can see this little rule here. I get some bad glare. My bad. Okay, so 12 times a 24 over 36. Well, let's see. This drops out. That becomes a 3. Doesn't this become an 8? I think I did that right. So in the end, this circuit is actually just equivalent to an 8 microfarad capacitor. With a 1.5 volt battery. There we go. All right. So this was figuring out the equivalent capacitance. You might be saying, why are we doing this? Well, it's on the quiz. Oh, I mean, there's actual uses. Yeah, that too. But okay, so here's the deal. We did all this work to combine this down to a simple circuit. Here's the trick. Why are we doing that? If you do this, remember that the last capacitor standing has the same voltage as the battery. By doing this trick, what we've done is we've taken something complicated where we don't know the voltage on these individual elements. It's too complicated for us. But if you get it down to just one capacitor and the battery, they do share the same voltage. This capacitor is in parallel with that battery. It's also in series with it, but that's tricky. Yeah, so the fact remains is that these two objects have to have the same voltage. Why? More on that later. Okay, so all of a sudden we have learned something. Right now we know, aha, I know the voltage here is equal to 1.5 volts. I also know that Q is equal to delta VC, and I know that U is 1/2 Q delta V for the capacitor. Is that still on the board? Yeah, it is. So the idea is this. Once you get down to the last capacitor, you know its charge, its voltage, and its energy. And from that point, we could start working our way back up the chart to figure out the charge, voltage, and energy on each of these. More on that in a second. I want to pause and see if, go ahead and ask any questions. Remember, a lot of you perhaps have seen circuits, and that's fine. Most of you probably haven't. So I know it's very hard and you think, man, I don't want to sound stupid by asking questions. Please ask questions. All right. You're not going to sound stupid. All right. I was just teasing Ryan earlier just because I knew he could take it. All right. So yeah, definitely ask questions on this. Anything? Awesome. And then let's start working our way back up then. Okay. And you could put them in the chat too. Maybe I'll even recognize it. Okay. Now I want to go, let's say I've learned all these numbers. I'm going to punch in a calculator really quick and figure them out. Okay. And so if I know the voltage is 1.5 and I know this is 8 times 1.5, that gives me 12. So I know that the charge on this one is going to be 12 micro coulombs. How did I get that? 1.5 volts times a microfarad. A volt times a farad is a coulomb. How do I know that? Here's the equation. Volts times farads equal coulombs. All right. Down here, the energy, I'm going to punch that in and see what I get. So I get 0.5 times the voltage, which is 1.5, times, what was the charge? 12 micros. So times 12. So I got 9 microjoules. Anybody else get those numbers? Hopefully you did. So that's the charge and the energy. So here's the big picture now. We know this is the equivalent capacitance. We know this is the voltage on the equivalent. This is the charge on the equivalent and the energy. I know that this amount of charge and that amount of energy are spread out in some complicated manner on all of these. So if I work my way backwards, this thing, when I figure out the charge on each one, right, hopefully that relates to this charge in the appropriate way. And when I figure out the energy, I know that the total energy of all of these put together should add up to 9 microjoules. So that's really our big check. The energy is a way to check your work going forwards. All right, let's read the notes on how these things work. So in this case, we know the following. Let me get this bigger again. Oh, there we go. So here's our rules. If we do a series capacitance, we did all this, we did all that. So we're actually done with this, and we did this. We finished that phase. So now what we're doing is, if you have a series, you could do these pieces of information. If you had a parallel combination, we're going to use these two pieces of information. So what do I mean by that? Let's look back at the step we took at each level and use the appropriate rule. Whenever things are in series, they have the same, whenever things are in parallel, they have the same voltage as the equivalent. And whenever things are in, sorry, dealing with Zoom. Whenever things are in series, they have the same charge as the equivalent. That's what I want you to remember. Parallel voltage. Just remember that. The other one. So take a look. These were using what? A series? When I combined them, was I using the series rules to get that 8, or was I using the parallel rules to get this number 8?
Series.
Series. So then these should have the same what? Do they have the same voltage as this, or do they have the same charge as this?
Charge.
Charge. So that means, aha, now I know each one of these has 12 microcoulombs. Got it? And so if I have 12 microcoulombs on each, aha, now I could use these rules again and get the charge and the energy. Wait, actually, we could use this one to get the voltage this time. I'm sorry. This time we know C, the capacitance in farads. I know Q, the charge in microcoulombs. And so I could use Q equals VC to solve for V. So I'm going to do that. If Q equals VC, that means delta V is equal to what? Q over C? So in this case, I hope you agree that means this is 1.0 volts. The micros cancel, and the 12 over 12 is 1. Now think. You could do the same thing over here. This is 0.5 volts because it's 12 over 24. And I'm not going to do the energy. I believe that you could plug in the numbers for energy later. And I'll try and write this up and finish the solution later. I didn't realize I'd skipped over this one when I was writing these this summer. So I'll write this up neatly and put it in the PDF eventually here this week. Okay. So, but yeah, we get these 0.5 volts. Check. I need a check on this. These two voltages should add up to the equivalent. Because these were in series, they had the same charge, and the two voltages should add up to this. They do. That's a check. Cool? Whew. Now we go from here to here. All right, if I go from here up to this situation, when I combined these two into that 12, I used the parallel rule. That means these two should have the same charge or voltage as the equivalent.
Voltage.
Voltage. So in this case, each of these has 1 volt, and this one's done. We already know everything about it now. We know its charge. We know its voltage. We could get its energy. Trivial. So at this point right here, this one now I know is 1.0 volts. This is 1.0 volts. So that helps me figure out the charge on each of those. Well, since Q equals VC, I know that this is 1 volt. I know that the capacitance, so this just tells me the charge on this one is 8.25, microcoulombs, and that's from Q equals delta V times C. Delta V is 1, and then I'm going to scoot this closer just in case. It's getting kind of bad there. So again, we have 8.25 here. That means this is probably 3.75 microcoulombs. Hopefully that makes sense, and I'll pause for a second. There's a pattern here, right? You're always just going, you work your way down using the series parallel rules, then you work your way back up using the same rules. And on the way down, you're combining the capacitance to make it as small as possible. On the way back, you're uncombining the capacitance and bringing the right quantity back with you, either charge or voltage. And so, yeah. All right. And there's physics reasons for that, which I'll try to elucidate after we get this rolling. But first, we got to learn the mechanics of doing this crap. All right, one last one. This red branch came from a series, so they should both have 3.75 micros. microcoulombs. And then from there, I could use, well, for each of those, I could say, well, if Q equals delta VC, I know that delta V is equal to Q over C. I know Q, I know C. I could get the voltages. And the two voltages should add up to 1. So in this case, I bet one of them, let's see, Q over C, this one's going to be, that's going to be 0.25. And this one's going to be 0.75 volts. And there you have all the numbers. I apologize that it's so hard. This is just a big problem to do on a tiny whiteboard. Wasn't that a, who was that guy? Chris Farley? Big problem on a tiny whiteboard? Oh, maybe that was the other thing. My bad. All right. All right. That's old school. Yeah. I don't know. Is this making any sense at all? Right on. Yeah, for sure.
So my phone kind of died, but basically we're just reverse engineering what we did in the first place while still using the same rules and equations
Right. So
to
if you
figure
did,
out all of our unknowns.
yeah, for example, in going from here to here, I made a parallel combination of those, right? So this, when I
Yeah.
combined these two, I did a parallel. Well, that tells me when I'm going back the other way, I can bring back with me the voltage. Why? Because the series parallel rules tell me, okay, when two things are in parallel, they share the same voltage as the equivalent capacitor. And I can't
Okay.
bring back the chart. Now, when I did this one to here, going between these two, I know that I did a series combination. Well, this one, somehow I did some math and I had 3.75 microcoulombs of charge here. Well, when I see that the series combination should, each of these capacitors should have the same charge as this. So I bring back the charge and the two voltages add up to 1. So why? Because the series rules tell us that. Is that cool?
And then you use that equation on the right to figure out which of those capacitors has how much of the voltage. Okay.
And then you check the two voltages should add up to what you used to have.
Okay. Okay.
And then like this one, when I did this, I know that the two charges should add up to what I used to have. So if you're doing a parallel combo, they have the same voltage, the two charges add up to the equivalent.
Okay.
So
cool.
Summarizing that, let's see if these rules are starting to make a little more sense here. The idea is you use this crap to figure out the equivalent capacitance. Then when you're working your way backwards, you either use this if you did a parallel rule or this if you did a series combination. And in all cases, you get this crap down here. Is that helping out a little?
Yeah. Yeah.
And why don't we do a quick simulation of this now? All right. I'm going to sit down for a second. Let me see if I can bring up a simulation here. All right. So here's the idea. This is kind of what we just looked at. I think there's some that already have multiple capacitors pre-wired here. So for example, we could do 3 of these in series, right? And we could do different capacitances, like a 3, a 2, there we go, and a 1. So now what I could do is I could bring out my voltmeter, right? And this is just measuring the voltage. And so the idea is I want you to think to yourselves, before I do this, I'm going to turn on the battery. Which one do you think is going to have the most charge? Which one's going to have the most voltage? Think to yourself or chat with your friends or whatever. So yeah, you can instant message them or Discord them or whatever you want. But yeah, I'm going to crank up the battery. You could see the capacitances. I have a 3, a 2, and a 1. Who cares about the 10 of those right now? Which one of these should have the most charge? Which one should have the most voltage? All right. I'll give you 30 more seconds, okay? To think about that. I need some water. I get no water. Oh, yeah. Oh, what a nightmare. Get this out of here. I was going to try and do a poll question. That's not what I want to be doing right now. Come on, you. There we go. It was going to be too much work to do that. All right, I'm going to go ahead and crank it up. All right. Hopefully you thought in series they all have the same charge. Now comes the fun part. When I measure these voltages, true enough, true enough. So here we go. Let's measure this one, C2 in the middle, all right? So this one, oh, whoops, you can see I've got the polarity flipped. Usually you put the black lead on the negative plate. So that's 0.409, and I'm going to write that down. The change in voltage as I go from one plate to the other, in this case, is 0.409 volts. Notice it's not exactly a third. They don't all have the same voltage. So if I go to the larger capacitor, what do you think should happen to the voltage? Let's find out. Oh, go ahead. What do you think?
Decreases.
Let's see. Exactly. Now, this may seem counterintuitive. You might think, oh, I thought Q equals VC. Well, remember, in series, they all have the same amount of charge. The larger capacitor requires less voltage to get the same amount of charge. Okay. So in this case, delta V is equal to what? 0.273. And so how much should be left for the last one? 1.5 minus that crap, right? So 1.5, whatever. Yeah, let's just go do it. So if I come down to here, all right. And so we see that the smallest capacitor actually has the largest voltage. And if you add those all up, it's probably really close to 1.5, perhaps off in the third digit where there's rounding. Okay. So, all right, looking pretty good. So they all have the same charge. And am I able to do that? Here's the stored charge on these ones. Oh, so that's the total stored charge. I don't know if it's giving me the this. Now I want to talk to you a little bit about why do these things have to have the same amount of charge? And think about it. These are made of metal. If this has a negative charge on it, that negative charge had to come from this piece of metal. Then there's a big air gap here. There's no way for these two plates to get their charges from anywhere else. So again, I'm looking at these two plates right here and right here. If you think about it, the electrons that are on this plate came from that plate. So that's why they have the same charge in series. Similarly, the electrons on this plate came from that plate. And finally, the electrons on this plate were pumped over there by the battery all the way around to there. All right. And so in series, they have to have the same charge because charge is not created or destroyed in the universe. Charge is conserved. We had conservation of mass in chemistry, conservation of energy in physics. We now have conservation of charge. So that's the physics behind this. Now, where does conservation of energy come into play? Think about this. If I start right here, and let's say I'm a charge Q, all right? You could say it's an electron if you want, but for right now, let's just say it's a charge Q. If I start here, the voltage is going to change. It's going to go up, and then I'm going to come back around. And if I get back to the same spot in the circuit, delta V of the entire loop has to be 0. Why? If not, you'd have an infinite stream of energy and everything in the world would explode. That doesn't happen. What? Let me try this on the board. Okay. So hopefully you got those numbers here. Let me have you think about it like this. All right. Suppose we didn't have this true. Let's say we started right here, and there's a capacitor here. All right. And let's say I start right here. You could call any point in the circuit 0 volts that you want. That's called ground, or your reference level. Just like when you're doing a drop the rock problem, you could call the bottom 0 or you could call the top 0. It's a reference level. So where we choose to call 0 in a circuit is completely arbitrary. It's completely our choice. I'm going to call this point 0 volts because it's convenient for me. If this is a 1.5 volt battery, let's do this. If I go from here to here, let's say this is 1.5 volts, and then we're going to come back down here. What I'm saying is, if you're an electron sitting here on this plate, if you're an electron and you move around this entire circuit somehow, I guess normally this is true with a resistor circuit, but let's do that. Let's say I have a resistor circuit, okay? We haven't learned what that is. But if you're an electron, let's see, this would be a plus plate, this would be a minus plate. You would think that electrons would want to travel this way. So let's say you have an electron traveling that way. As it goes around, if you didn't have delta V equals 0 around the entire circuit, each time it goes around, there'd be some small delta V, which would be multiplied by E. You'd get a small change in energy. And so if you had delta V equal non-zero around an entire loop, each time an electron makes the circuit, it would gain a bit of energy. That means this thing would gain energy every single time it loops around. Eventually, you'd have an infinite amount of energy, and this thing would explode. That doesn't happen. So what do we know from experience? We know that when you go all the way around the circuit, the change in energy has to be 0. And so conservation of energy tells us the voltages around this circuit add up to 0, the voltage differences, potential differences. So anyways, the rules that I'm giving you come from the physics equations. Charge is conserved, energy is conserved. More on that when we get to resistor circuits. So yeah, you could do that. Go for it. All right. So just be aware of that. Let's go back to this crazy looking thing. These start to be more like the types that I would put on an exam, right? Where you have a mix. And so you could imagine in this case, you could have different capacitances on each one. Whatever. And so the idea is we see that you get these complicated circuits where these two capacitors, C1 and C2, are in series. So they have the same charge. This one has the same, if you combine these into one mega capacitor, C12, C12 and C3 actually have the same voltages. So, whoops, if you look at that blob, right, these two things are basically in parallel. And so you'd see that this voltage difference should be the same as this. Let's see if that's true. Again, what I'm saying is, oh, geez. The voltage across this one happens to be 1.5. Well, the voltage across this one is 0.5. The voltage across this one is 1. The voltage across both of them put together is 1.5. We see that these two have the same, we see that this one and this one have the same charge. Their voltages add up to the equivalent. Right? And then here comes another one like this. This one gets a little bit sneaky here. So let's change these. And we see something very complicated looking here, right? Every capacitor has a different amount on it. Right? And so in this case, let's make this 2 or something. There. So now the idea here is if I was attacking this problem, I'd say, oh, these two are in parallel. Now notice that when you put those two in parallel, the equivalent capacitor has the same amount of charge as this upper one, right? Looks like there's 9 here plus what is that? 16 there. So 9 plus 16 is 25, which is what this one has. So again, the total charge on these two adds up to make that one. And these two have the same voltage as each other. We get these complicated rules. I'm babbling a lot. I don't know. Is this making any sense at all? I don't know. Questions? All right. Okay. Oof. Let's see where we are at.
So the strategy for these problems is going to be simplifying what's in a series first, so you have one less capacitor to look at, and then look at what's in parallel.
Right. Or, well, it just depends. So
Okay.
let me, yeah, you're right. You're going to do one of those things. You're either going to do series or parallel. So let's take a look down here. We just did that one kind of. So this is a great question to do early on. You can see that's a parallel circuit. Here's a series circuit. You can kind of take your guess based off what we've done. So maybe do that after class before this gets away from you. All right. And now look at these crazy looking circuits here. These ones look pretty gnarly, right? So it gets hard trying to tell if circuits are series or parallel, which relates to what Corey was talking about. It turns out there's a trick for these. I'll show you that in a minute, but you can see there's all these different cases. Are they in series or parallel? Let me get to another one. Here's one. Here's a couple of nasty looking ones. So the idea here is, I think that was Corey asking, right? So
Yes.
Corey, if you don't mind, stay unmuted for a second. When you look at this ugly capacitor circuit, where would you start? And would you start with series or parallel? Which capacitor number? And take a guess. It's okay to be wrong.
I would start with C2 and C3.
I would. Would you use series or parallel for that?
Series.
Excellent. After you do that, what would you do next?
Would you have a choice then between, I
Nope.
guess, C2? Oh, no, you don't. Okay.
So what would you think if based on there's no choice?
Well, they're going to be in parallel now.
With
or at least
what?
I think they would be.
With what?
C4?
That's right. So I would do this next.
Okay.
And then after that, what would you do?
Would look over at C1.
Yeah. And then would they be in series or parallel with C1?
Parallel.
Series.
Oh, that's weird. Okay. I see what
Yeah.
you're saying. That is okay.
It
I see what
is
you're
tricky,
saying. Now it moves
and
over
so
there. Okay.
I'm going to show you this trick right now for telling the difference between these circuits. And so that was a good attempt. Everybody give him a round of applause for being brave there and toughing it out. Thank you, Corey. All right. So let's see here. Let me show you a cool trick that I learned that some students really like. These get really tricky to try and understand if it's series or parallel. All right. So in this case, let's look at this one that we just were puzzled on. Corey, do you know what number that was? Can you tell me? Was that 25.11? I forget what it was. Actually, I have it somewhere. 25.11. I got it.
Yeah.
You're good. So this was 25.11. Okay. And now you see where people are going to get hung up on the quiz. Everything seems really easy, except if you screw up one series or parallel rule because you're in a rush to get through it. And then you just think, oh, crap. So you really have to practice this so that you have time to sit there and think. This was C1, C2, C3, C4. Now, there's an old trick you can do. You can slide things wherever you want. And so if you imagine, take out the battery, grab the two ends and stretch the circuit vertically, what would happen? Well, if you stretch this vertically, wouldn't C1 start coming up here? So what I did is I took this point and this point, I took out the battery, grabbed it, and I stretched it. Well, to do that, C1 ends up way up here. This is still C2. This is still C3. This is still C4. And now, Corey, does it look more obvious that now if I put the battery back in, Does that
Yeah,
look
that
a
makes
little
a
more?
lot more sense.
And that's a cool trick you can use, the grab and stretch it vertically. And that works all the time. So yeah, take a look at a complicated circuit like 25.15. Let me see if I have that there. So
Yeah, that looks awful.
and it turns out it's not, but yeah, or even like 20, right? If you stretch this, hopefully you see that C1 and C4 are in series, C2 and C3 are in parallel, and then the combination 2, 3 is in series with 1 and 4 as well. But look at this one, right? If you stretch this, it's not that bad. This one and this one. Well, let's try and do the stretch technique on this one. So why don't you get, rather than me telling you, oh, it's not that bad. Of course, it's not that bad for me. I wrote it. It's probably really bad for you. So why don't we try you seeing if you can just stretch that and get the right orientation when you stretch that. I'll do it on the board too. What is this, 25.15? And then we'll call this a day after this probably. Yeah, it's time to go, right? So if you have to take off, take off. This will be in the end of the live stream. You can just go back and watch it later if you got another class. But this is the kind of stuff you can't get from reading the workbook solutions very easily. So that's why we want to do it. The rest of this is pretty easy in the workbook. Okay. Okay. So let me see here. So what I'm going to do is I'm going to grab this, disconnect the battery and stretch it right here, right? And stretch it right here. So in this case, I see there's a wire coming out the bottom and a wire coming in the top. Coming from here, I see that there's C2 right here and C2. How would I put some colored dots on this? There's the blue dot right there. Here is a red dot right here. Now I know there's red, green, colorblind, so let's do a hollow green dot. That way, if you're red, green, colorblind, you could do this too. So notice C2 is always between the red dot and the blue dot. So that's just done. All right. Now C3 goes down here. Ooh, I see that there's a C5 coming out here, right? See that C5? It's one side of it is connected to there, and then the other side has to go over here to some kind of green dot. These dots are called nodes. Okay. So this is the red node, the blue node, and the green node. Now I see that there's two wires coming out of that one. And I see that there's two wires coming out of here. So now all I got to do is get this lined up. Looks like this one is C3, right? And this one over here looks like C1 and C4. C4, man, that capacitor is the bomb. So bad. All right. Anyways, now it still doesn't look that good. You could stretch it even farther to see this even better, but I can already tell, I don't know if you can, these are in series. This series combination is in parallel with that one. Then this blob is in series with that one. And then all of this blob over here, that's the blob technique, is in parallel with this one, right? So if I do one more picture down here, sorry, it's getting out of whack. Now I'm going to tighten this up. This is C2. This is C. That's C3. This is C1. This is C4. This is C5. And now it's easy. Again, where are our nodes, right? This is the red node. All of this So sometimes in an electronics class, they'll call this a super node. Everything there was connected to the red point. Down here, this blue is everything there. And then green is this intermediate node. I hope that makes a little bit of sense. And I don't know, I wouldn't. So Phil, do you agree it's not what you said? It's some, well.
Yeah, it simplifies differently.
So what would I do? I'd start with 1, 4, combine them in series. Next, combine that equivalent with this one in parallel. Then take this blob and combine that with this one in series. Then take that and combine it in parallel with C2. Yeah. And then, all right. So that's cool. And, oh man, we'll pick up there next time. All right. Give those a shot, struggle with the solutions, and you should keep the solutions open for the first couple of these ones. And then hopefully by the time you get to say 14 and 15, you can put them away. 25.13 is another problem I did where I actually drew the stretching at home for you. So yeah, you can get, let me see if I'm lying to you. So you can see I tried to do these. And so some of these tricky ones, I tried to draw the pictures for you just because I want you to succeed. So it's, yeah, there's some tricky ones. I hope this is helping you draw those. So if you don't understand the pictures in here, definitely come talk to me. Where's that weird one? There's one where I tried to do the stretch technique. So 25.13, you can practice that one. And you can see I try to do that as best I can. All right. Oh, I forgot to screen share. Shit. All right, whatever. All right, let's stop the live stream there. It's not getting